Welcome back. In my previous video I had seen Cauchy's integral theorem is the easiest way to find integration of any path. And we all of us know if f is analytic in a simply connected domain, then integration fz dz is actually independent of path C in the domain D. Today I will say for which functions and domains integration fz dz is independent of contour C. Actually today's goal of this lecture. Today I will see this theorem. Suppose that f is continuous on a domain D, then the function f has an antiderivative if and only if integration over the closed contour is independent of path. In my previous video I had seen if function is analytic in a simply connected domain, then integration fz dz is independent of path C in D. In my previous video I had seen this. Today I will see if f has an antiderivative, then integration is independent of path, and obviously f is continuous in a domain D, or conversely, obviously this is the if and only condition. If integration between the contour fz dz is independent of path, then that implies the function has an antiderivative in the domain D. This is actually today's goal of this lecture. That means today I will say for which functions and domains integration fz dz is independent of contour. At first, since all part depends on antiderivative of function, so at first define what is the antiderivative of function. Now I will see what is the antiderivatives. Antiderivatives is, suppose a function f is continuous on a domain D, and antiderivative of a function f is a function capital A, such that f prime z equal to f of z. Here f of z is the original function, and this is true for all z in the domain D. If for all z in the domain D, f prime z is equal to original function f of z, then we can tell antiderivative of the function f is the function capital A. As for example, del z cos z equal to minus sin z. So, cos z is the antiderivative of minus sin z. Similarly, del z of sin z equal to cos z. So, sin z is the antiderivative of cos z. I hope my all viewers have understood what is the antiderivative of a function. Okay? Well. Now I will see tonight's theorem on antiderivative. Let fz be continuous from on a domain D, then fz has an antiderivative capital Fz. Second, integration z1 to z2 fz dz equal to, since fz is the capital Fz is the antiderivative of fz, so when I will apply integration, then this would be, obviously since this is equal to capital F prime z, so after integrating this value would be capital Fz2 minus capital Fz1, and this is true for all C, for all contour starting from z1 and ending from z2, such that C entirely lies in the domain. That means when a function has an antiderivative, then the value of integration is path independent. That means the value of integrals does not depend on the path. We can choose such type of any type of path. This is depend only the starting point and end point. Now I will see proof of these two theorem. What is the proof of this theorem? Let's see. Let capital Fz be an antiderivative of small fz. That means f prime z equal to f of z, and this is true for all z belongs to D. And let C be a smooth curve from z1 to z2 which lies entirely in the domain D. Then integration along this smooth curve f of z dz. F of z means, since here f prime z, so we can write this as integration a to b f of z t times z prime t dt, and this is means f prime z, capital F prime z. So this is integration a to b f prime z t times z prime t dt, which is equal to integration a to b dt of f of z t dt. This means this, we all of us know. Now after integrating, this value is obviously f of zb minus f of za, and f of zb means z2 and f of za means z1. I hope my all viewers have understood. If f has an antiderivative, then this integration is same as capital Fz2 minus capital Fz1. This is actually known as the fundamental theorem for contour integral. The statement of the theorem is if f is a continuous on a domain D and capital F is an antiderivative of the function f in the domain D, then for any contour C in the domain D with initial point z0 and terminal point z1, then integration along this curve fz dz equal to capital Fz1 minus capital Fz0. I hope my all viewers have understood. This is this theorem. This is the fundamental theorem for contour integral. Now I have got in two ideas. When the domain is simply connected and function be analytic, then that imply independence of path. This is one result which I had seen in my previous video, and from today's idea I have got this idea. When a function has an antiderivative, then by fundamental theorem of contour integral we can tell independence of path. We can tell about independence of path. Now find the integration z square dz of following contour from 1 to minus 1. Now I will see what is the integration of z square dz of following contour from 1 to minus 1. Because here actually we have to check the first endpoint and second endpoint along this contour. So for this integral, if not only for this integral, for all integral, since this is the path independent, so we can take easiest contour, because here only depend only the first endpoint and second endpoint. Notice for this integral, since here the domain is simply connected and z square is analytic, so here which path would be easiest method? Notice this path would be easiest. Now find the integration z square dz of following contour from 1 to minus 1. Now I will see what is the integration of z square dz of following contour from 1 to minus 1. Find the integration z square dz from 1 to minus 1. Means z square is analytic. So at first I will find the integral by Cauchy's integral formula. Since I have seen this is the easiest path, and since this is the half circle, so integration z square dz, since z square is analytic, at first take the contour integral, consider z equal to e to the power it. Then find the value. This value would be integration 0 to pi e to the power 2it times e to the power it, I times e to the power it dt. Just common I from outside, this value would be 0 to pi e to the power 3it dt, and this value is I e to the power 3it over 3I from 0 to pi, and this value is minus 2 over 3. This is the contour integral, but since z square is z square has an antiderivative, so we can here apply fundamental theorem of contour integral, and this is, since the integration 1 to minus 1, so 1 to minus 1 z square dz, here the antiderivative of the function fz means z square is obviously z cube over 3, and the integration from minus 1 to 1, and this value would be minus 1 over 3 minus 1 over 3, this value would be minus 2 over 3. I hope my all viewers have understood the method of antiderivative. If a function has an antiderivative, this is the most easier method than the Cauchy's integral, I hope. Now I will say fz equal to 1 over z. We all of us know antiderivative of 1 over z is log z. But in the complex plane, log z has multiple branches. Why? Because real exponential function means e to the power x. We all of us know this is the 1-to-1 function with inverse function log, and log defined from 0 infinity to r called the natural logarithm, and this is the in real variable. But in complex exponential function, e to the power z means e to the power x times cos y plus I sin y. Obviously, e to the power z is periodic function with the period 2 pi I. We all of us know. Actually, I will say why log z is multiple, why log z in complex analysis has multiple branch. W equal to u plus iv. We all of us know, and w equal to here log z. Inverse function of log z would be e to the power w, and e to the power w means e to the power u plus iv, which is equal to e to the power u times cos v plus I sin v, where u, that means u equal to log mod z and v equal to, if we consider w equal to log z, u equal to log mod z and v equal to the argument theta p plus 2 pi n, and this is true for all value of n. Now notice the picture. That means log z means log mod z plus theta p plus 2 pi n times I. This is the log z, which is denoted as capital log z equal to small log mod z plus theta p plus 2 pi n times I. W equal to log z. Notice the picture. Its inverse obviously would be to the power w. And here the real x and here the imaginary y. And w after transformation this would be log z. That means this is the real u and imaginary v. Log z means log absolute value of z plus theta p plus 2 pi n times I. Log absolute value z means, consider this is the log r, this is the radius and this would be this type of line, but phase angle of w, it could be different. Angle would be different because here log z means log absolute value of z plus theta pi plus 2 pi n times I. Consider this is theta p, this is theta p plus 2 pi, this is theta p plus 4 pi. Similarly, for negative value, it would be different value. Therefore, for different value of theta, the value of here the value is same. It could be theta p plus 8 pi 6 and any another. Also, it could be theta p minus 2 pi minus 4 pi, so on. But here the value is same. So that means for infinite value of w, here I will got only one value and this point is z. So log is very interesting. For infinite value, there is only one value. This is the z. So if I consider r equal to 2 e to the power I theta, this type of region, in this region fz equal to 1 over z, whose has a antiderivative log z, which has multiple branches. So integration fz dz, where fz is 1 over z, in this region, if we consider this type of region 2 e to the power I theta, not be defined. I hope my all viewers have understood this is clearly. Okay? Oh well. Now my question, then how can we evaluate this integral? Just this integral in two parts. In C1, minus pi, theta lies between minus pi over 2 to pi over 2. In C2, theta lies between pi over 2 to 3 pi over 2. For C1 equal to 2 e to the power I theta, I have got fz equal to capital log z, where mod z greater than 0, then capital log z means log r plus I theta. Then integration along the path C1, fz dz means along the path C1, here integration (1 over z dz) and antiderivative of 1 over z is capital log z, and along the path C1, here value is minus 2i to 2i. Therefore, this value is log minus 2i minus log 2i. And log minus 2i means this value is theta lies between minus pi over 2 to pi over 2. Therefore, log minus 2i means small log 2 plus I minus pi over 2 minus log 2 I pi over 2, and this value is I pi. Okay. Similarly, along the path C2, fz dz equal to C2, along the path C2, 1 over z dz, and the antiderivative of 1 over z is log z, where mod z greater than 0. And this value would be, sorry. This value similar to before, log minus 2i minus log capital Log 2i. And here theta lies between pi over 2 to 3 pi over 2. So this value would be small log 2 plus I pi over 2 minus small log 2 minus I 3 pi over 2. Okay, and this value would be similar to before. This value would be I pi. I hope my all viewers have understood. Therefore, integration z square dz from 1 to minus 1 means, here I have considered the path c equal to e to the power 2 e to the power it, where t lies between whole circle means 0 to 2 pi. Now that means here it would be the whole circle, and here I have just this part as c1 c2. Therefore integration along c means obviously integration along c1 plus integration along c2. Then this would be whole circle. This is the c1 and this is the c2, and this is the whole circle c. Then the value of integration along c would be, for fz dz along the curve c means along whole curve, this is equal to fz dz along the curve c1 plus fz dz along the curve c2, and this value is equal to I plus I pi, which is equal to 2I pi. I hope my all viewers have understood this type of question. Okay? Oh well. I will stop here. In my next video, I will discuss this type of question and complex analysis, another part of complex analysis. But at first, I will highly recommend you please see today's video with pay attention, because this part is very important for higher study. Okay? See you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.